So today I will be talking about verifying networks with symbolic execution and temporal logic. So our network verification goal is to take a data plane snapshot of a network topology as well as a user policy which expresses some intended network behavior and verify that the topology complies with the policy. So we've done a few steps in this direction using SymNet and Cephl, and I will briefly tell you what's that all about. So our approach consists in taking the data plane snapshot and converting it to a network model. And the modeling language that we use is Cephl, symbolic execution friendly language. So this is a very simplistic imperative language which has been specifically designed for symbolic execution. So once the model has been built, what we do is we select an input port and then perform symbolic execution starting at that port. So the result is a set of execution paths which describe all possible routes which a packet can take through the network. And to do symbolic execution, we use SymNet, which is a symbolic execution engine specifically designed for Cephl. So SymNet can actually run in seconds on enterprise networks, and this is mainly because of the language design of Cephl, and you can find out more details in our paper listed below. So, if the objective is to check reachability, for instance, between ports A and D of the network, then we simply run symbolic execution. We look at the output, at the execution paths, and we manually inspect them. And if we find a path on which port D is reached, then we can report that such a policy is satisfied. And if you have any questions, you can stop me, I guess. So if we want to check other policies, so this one is actually our CS department policy. PCs in VLAN labs should not talk to those in VLAN office. So it may be obvious by now that checking such a policy is not straightforward using the previous recipe. So we need to establish a few things. For instance, to verify this policy, we need to consider several ports. So we may need to run symbolic execution at several inputs. And some fields of the symbolic packet should be symbolic while others should be concrete. So we need to establish that. And also, it may be obvious that exploring the entire model is inefficient. So having said that, symbolic execution is in itself cannot deliver end-to-end verification by itself, so we need a new ingredient, a policy language. So how would such a policy language look like? So we've looked at several existing policy languages, especially for SDN, such as Merlin, and also others, such as NetPlumber. And they share a main limitation with regard to expressiveness. So they have limited expressivity. I do not have enough time, but if you look at the paper, you can see that there are interesting policies which cannot be expressed in such languages. So then we turn to other languages which are used to express properties of transition systems, and especially CTL, computation tree logic. And based on CTL, we built NetCheck. So how does NetCheck look like? It has path operators. They are evaluated at certain ports of the network, and they can express statements regarding existing paths that start at that port. And it also contains temporal operators, which are evaluated with respect to one execution path, and they express properties which hold at specific ports or at all ports of the network. And just like with CTL, in NetCheck, each temporal operator is directly preceded by a path operator, and this actually guarantees good complexity in terms of verification. So we've implemented NetCheck as an extension to the SymNet execution engine, and what it basically does,
Can you say the semantics of globally, please?
Sure. So globally, phi holds if on each state of that path, phi holds. So at each port of the path, it's always, yeah. So NetCheck performs symbolic execution and at the same time monitors the satisfaction state of a formula. And NetCheck does not rely on traditional model checking algorithms, so it actually exploits the fact that our model is a tree, a symbolic execution tree, and implements some nice features which I may be able to talk about. And in the end, NetCheck need not explore the entire model to validate the policy. So let me use a very simple example to show you how NetCheck works. So assume that all traffic is generated at port A of this very simple topology, and I will first start off by showing how symbolic execution works in this very simple example. So first of all, we need to construct a model of the network. So in such a model, each device is described as an element with input and output ports, and we assign Cephal code to each specific port. Now, the input of symbolic execution is a symbolic packet. Such a packet contains symbolic header fields, that is, fields which can have any possible value within their range. So assume that this firewall will only allow traffic from the source TCP port 80. When symbolically executing this code, we will see at the output a symbolic packet with the appropriate constraint added to the source TCP field. And further on, this symbolic packet will be forwarded to the input port of the router. So to model the routing conditions in Cephal, we use a conditional instruction, and conditionals branch symbolic execution. So if the input is this one, symbolic execution of the if if instruction will produce two execution paths. On one path, the condition is added, so destination IP equals A, and the packet is forwarded on port 1, while on the else branch, we will see the complement of the condition, so destination IP different from A, and this symbolic packet will be forwarded on port 2. Finally, assuming that the proxy modifies the destination IP, we use the assign instruction to capture this, and assign on a symbolic packet will simply override existing constraints. So now you see that the destination IP is equal to B instead of A as before. So the output of symbolic execution, again, is a set of execution paths. We have two here. On one path, we have the destination IP equal to B, and on the other, we have the destination IP different from A. So moving on to NetCheck, let us suppose we want to verify a simple policy, that is B reachable from A? So we can express this policy using the following formula. There exists a path on which at some point port equals B. So to check this, we perform symbolic execution starting at A, recall that symbolic execution branches at the router, and following the first path, we will eventually find that the port becomes equal to B, and therefore the formula is validated and symbolic execution can stop now without exploring the other path. So if we look at a more interesting policy, does the destination IP change? So we can express that as follows. So first of all, just after injecting a symbolic packet, we need to add this code which allocates a new variable called initial, and then it assigns the destination IP to initial. So having done that, we can verify the formula on all paths, and at each point, the destination IP equals initial. So to verify this formula, we need to consider at most all the paths, and at each hop, we need to check that the state property destination IP equals initial. So to do that, we build the complement of this condition, and we add the complement to the set of constraints built by symbolic execution at port 1 of the firewall. If the combined set of constraints is unsatisfiable, then the original formula is true. And we do this verification at each point, at each hop in the network. And finally, at the output port 1 of the proxy, we find that the complement of the constraint is violated. Okay? So this means that the sub-formula globally destination IP equals initial is false on this path, therefore the entire formula is false. So we have a few results, we have a few preliminary results regarding NetCheck. So we've run it on our CS department core middle box, which is an adaptive security appliance, and we've used several formulae, and the ones which explore all feasible execution paths will actually find 4 such paths, and each path will contain approximately 100 instructions. And what we see is that NetCheck verification actually scales as well as SIMNet, so we're actually not paying as much. And in many cases, we can actually pay less for NetCheck verification because we will not explore all paths. And we've also played around with NetCheck to express more interesting queries such as TCP end-to-end connectivity. And NetCheck is not perfect, and it's not an end result. So first of all, NetCheck borrows from CTL, the unfortunate property that it is difficult to use by people which don't have background in temporal logic. And NetCheck does not support natively the ability to perform symbolic execution at several ports of the topology. And for certain policies, it may be the case that we need to update the network model and add certain behaviors at some points. For instance, add a behavior which models a TCP response. So we need to modify the network model, and NetCheck does not natively support that right now. So we're working on these various issues to improve NetCheck. Thank you.
Questions? Is it even possible to verify the sequence of which the packet differs?
Could you repeat the question for the benefit of people?
Right. So again, the
sequence of the packet from A to B, is it possible
the
to
sequence
verify?
What exactly are you referring to when you're saying sequence?
So that is going first through the firewall and then through the
Yes. So we can actually build a policy which captures a sequence of routes which the packet should take. So you can express that using NetCheck. Yep. There are a few operators which I did not include, such as next and until, which are also part of the syntax, and you can actually play around with next to express what you mentioned. Yeah.
So I have a question about the formulas. A two-part question. One is how complex were the formulas that you looked at? And the second is whether there were any patterns to these formulas, like certain kind of operator prefixes that show up, or whether they evolved into certain.
Okay, so what kind of formula can you use to on NetCheck? So actually, you can use any kind of CTL-like formula. The only restriction is regarding nesting. So each temporal and path operator nesting. So each path operator has to be directly preceded by a path one. But we've used also complex formula which also check certain properties which must hold on all paths. So more complex queries than the ones shown here. Yeah. So we can do that. We have done that.
And the examples you looked at, did they suggest that a more specialized form of CTL might be adequate here, or would full-blown CTL be?
Well, actually, we believe that we can, since the model is actually a tree, we believe that we can extend CTL and play around and check formula which are not necessarily CTL, so formula which violate the constraint added here. So we can do that in the same time with this basically almost the same algorithm. But we have not found realistic policies which actually would require that. So that would be an option. So we can extend CTL actually. I'm not sure if by restricting CTL we can actually get a perceivable benefit.
Okay, great.
Thank you.
Wow, this is fantastic.